What if the most promising world beyond our solar system just whispered something back to us? Not a signal in the science fiction sense, not a flashing beacon, but something quieter, deeper, hidden in light itself. James Webb has been staring at the TRAPPIST-1 system, a small red dwarf star about 40 light-years away. And what it has detected on TRAPPIST-1e is forcing scientists to slow down and look again. This isn't just another exoplanet update. This is about one of the most Earth-like planets we've ever found. And if you care about the search for life in the universe, this might be one of the most important developments of the decade. Before we go further, if you're fascinated by real space discoveries and not science fiction, take 1 second and hit like. It tells YouTube that serious space exploration still matters. Now here's why this matters. TRAPPIST-1e sits in the habitable zone of its star, the narrow region where liquid water could exist on a planet's surface. It's rocky, it's roughly Earth-sized, it orbits close enough to receive warmth, but not so close that it should be completely stripped. For years, scientists have debated whether it could hold an atmosphere, and without an atmosphere, there is no surface water, no climate stability, no long-term chance for life as we understand it. The James Webb Space Telescope doesn't take pictures of aliens, it studies starlight. When TRAPPIST-1e passes in front of its star, a tiny fraction of that starlight filters through the planet's atmosphere, if one exists, and hidden inside that filtered light are chemical fingerprints. That's where things get interesting. Early data hinted at something unexpected, signs that TRAPPIST-1e may not be a bare, airless rock after all. If confirmed, this would dramatically change our understanding of the entire TRAPPIST-1 system, because if one planet there can hold on to an atmosphere under the intense radiation of a red dwarf star, maybe others can too. And that possibility opens a door that scientists have been cautiously pushing for years.
To understand why this detection is so significant, we need to talk about red dwarf stars. TRAPPIST-1 is much smaller and cooler than our Sun, but it's also far more active. Young red dwarfs can unleash powerful stellar flares, blasting nearby planets with radiation that can strip atmospheres over time. For a planet orbiting as close as TRAPPIST-1e does, this is a serious problem. Many astronomers once believed that planets in such systems would end up like scorched rocks, their atmospheres long gone. That's why Webb's observations matter so much. Using transmission spectroscopy, the telescope analyzed the spectrum of light during multiple transits of TRAPPIST-1e. Scientists weren't just looking for oxygen or methane, the classic biosignature gases. First, they wanted to answer a simpler but more fundamental question: is there any substantial atmosphere at all? Some early interpretations of the data suggest the planet is not wrapped in a thick hydrogen envelope like a mini Neptune. That's good news, because TRAPPIST-1e was always thought to be rocky. Even more intriguing, certain wavelength patterns hint at the possibility of a secondary atmosphere, potentially composed of heavier molecules like carbon dioxide. A carbon dioxide-rich atmosphere wouldn't mean life, but it would mean climate regulation is possible. On Earth, carbon dioxide plays a critical role in maintaining surface temperatures. Without it, our planet would be a frozen world. With too much of it, we get a runaway greenhouse effect like Venus, so the balance matters. If TRAPPIST-1e has managed to maintain a stable, moderate atmosphere despite orbiting a volatile red dwarf, that tells us something profound. Rocky planets around small stars may be more resilient than we thought. And since red dwarfs are the most common type of star in the galaxy, that dramatically increases the number of potentially habitable worlds. But here's where things become even more complex. Detecting an atmosphere is only the first step. The real challenge is distinguishing between a lifeless atmosphere and one influenced by biology. On Earth, life has fundamentally reshaped our atmosphere. Oxygen, for example, is highly reactive. Without constant replenishment from photosynthetic organisms, it would disappear over geological timescales. Scientists studying TRAPPIST-1e are not claiming they've found oxygen oceans or alien forests. What they're saying is more subtle. The data does not support a completely airless world. That alone shifts the narrative. Some models even allow for the possibility of cloud layers or heat redistribution mechanisms that prevent the planet's day side from overheating while the night side freezes. Because TRAPPIST-1e is likely tidally locked, one side permanently faces the star. For years, critics argued that such conditions would make stable climates impossible. But newer climate simulations suggest otherwise. If the atmosphere is thick enough, winds could transport heat efficiently around the planet. That would create a more temperate zone along the terminator line, the boundary between day and night. Imagine a world where twilight never ends, where temperatures remain stable enough for liquid water to persist. It sounds exotic, but physically plausible. Webb's data is still being analyzed, refined, debated. No one is declaring victory in the search for life, but the absence of evidence for a thick hydrogen envelope, combined with hints of heavier gases, keeps TRAPPIST-1e firmly in the conversation as one of the most compelling Earth-sized exoplanets ever discovered. So, what happens next? James Webb will continue observing transits, gathering more precise spectrum, reducing uncertainties. Future missions may build on this work, using next-generation telescopes designed specifically to hunt for biosignatures in Earth-sized worlds. But even now, TRAPPIST-1e represents something bigger than a single dataset. It represents a test case for one of astronomy's biggest questions. Are habitable environments common in the galaxy, or is Earth a rare exception? If a rocky planet orbiting a volatile red dwarf can retain an atmosphere for billions of years, then the Milky Way may be filled with stable, temperate worlds. Worlds that are not copies of Earth, but variations on the same theme. And that changes how we see our place in the cosmos. We are no longer asking whether planets exist beyond our solar system. We know they do, thousands of them. We are asking whether any of them can support complex chemistry over long timescales, whether any of them developed oceans, weather systems, maybe even biology. TRAPPIST-1e is not confirmed to host life, but it has just reminded scientists, and all of us, that the universe still holds surprises in the faintest traces of light. And sometimes, the most exciting discoveries are not loud announcements, but quiet signals that force us to reconsider what is possible.